e equals the sum from k equals 0 to infinity of 1 over k factorial, right? So what about e squared? Well, that's just equal to, if you can see, each of my terms will now have two denominators. So now it will be the sum to infinity of k and j equals 0 of 1 over k factorial j factorial, if that makes sense. And the reason for this is, well, we've got 1 plus 1 over 1 factorial plus 1 over 2 factorial. And the way we expand brackets, if you want to look at the precursor to the binomial expansion video, the way we expand n brackets with any number of terms inside them is by finding the sum of all megaterms. And here my megaterms are going to be 1 over, say I've got 1 over k factorial here. A megaterm is going to be of the form 1 over k factorial for some non-negative integer k. Well, this could be 0 factorial and that's 0 factorial. And then I've got another with not necessarily distinct, but most times it can be distinct, 2k in this bracket times 1 over j factorial. And in fact, I'm just going to let this be the sum to infinity of from j equals 0 of 1 over j factorial, because it's the same thing. Instead of k taking every value from 0 to infinity of non-negative integers, now I've got j taking all those values. But k and j both simultaneously take all values from 0 to infinity. And what I mean by that is for every value of k, j takes a value from 0 to infinity and vice versa. So for k equals 0, there's 1 over 0 factorial times 1 factorial, 0 factorial times 2 factorial, etc, etc, etc. And what's interesting about this is now I can say this is the sum as from 0, k and j equals 0 to infinity of, well, 1 over k plus j factorial times k plus j factorial over k factorial times j factorial. And this, you can see, is kind of in the form of the binomial coefficients, and indeed it is. So we've got this is the sum from here, and now I'm going to let n be greater than or equal to k equals 0. That means n can be 0 only when k is 0. So like when n is 1, that means k is either 0 or 1, etc, etc, etc. This means that j equals n minus k, by the way, just to avoid confusion. But for the binomial coefficients to properly be followed, n minus k and k have to be greater than or equal to 0 and non-negative integers. So now we've got, this is 1 over k plus j is now equal to n, because j is equal to n minus k. This e squared is equal to the sum from k equals 0 to infinity, where n takes all values greater than or equal to k for each value of k, of 1 over n factorial times n choose k. Instead of me looking at k now, how about I look at n? So n equals 0. Well, 1 over n factorial, since k takes all values from 0 to n that are less than or equal to n, this means for n equals 0, for any value of n, the sum of all values that are multiplied, all binomial coefficients that are multiplied by 1 over n factorial is, well, any binomial coefficient with n as its numerator. So n choose 0, since k takes all values from 0 to n. We've got 1 over n factorial times n choose 0 plus n choose 1 plus n choose 2 plus ... plus n choose n, and this is all multiplied by 1 over n factorial. So a nice thing to note is, if I replace x and y with 1 and 1, I end up with this being the sum from k equals 0 to n of n choose k, because these two are always 1 regardless, and multiplying by 1 doesn't change the value of anything. So that means all of this is actually equal to 2 to the power of n. So that means that e squared is equal to the sum from n equals 0 to infinity of 1 over n factorial times 2 to the power of n. And now you can see how we've got a different type of expansion for e squared. So instead of n, now I'm going to replace this with k. So this is 2 to the power of k over k factorial. That's what e squared is. But if we notice here, e is equal to the sum to infinity from k equals 0 of 1 over k factorial. And well, 1 to the power of k is equal to 1 for all non-negative integer values of 1, right? So we seem to have a sort of pattern forming. And in reality, the definition of what e to the power of x is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, etc., etc., etc. And it's an infinite series, and it's kind of like an infinite degree polynomial, which is kind of weird to wrap your heads around if you've seen graphs of e to the power of x. From k equals 0 to infinity of x to the power of k over k factorial. And that follows with e and e squared. And now I'm going to show you that this satisfies all the power laws and definitions, and we can get all the power laws and definitions from this identity. And what's good about this being my defining with this expansion of e to the power of x, now I've got a way to define the power function for all values of x, including irrational values, including pi, for example. So if e to the power of x is equal to this infinite polynomial series for all values of x, for this to be true, all these power laws have to be possibly derived with a base of e. And also, if I multiply x e's together, where x is a positive integer, this should follow. And it does seem to follow for e squared. Suppose the definition of e to the power of x is this infinite sum, and that's how I define powers, or the powers of e, I should say. If that's my true definition, well, that means all these power laws have to be able to be derived from e to the power of x. So let's try show that. E to the power of x plus y is equal to the sum from k equals 0 to infinity of x plus y to the power of k all over k factorial. And since k only takes non-negative integer values, I input k equals 0, k equals 1, k equals 2, k equals 3, but I never input a fraction. I never input k equals -5 or -1, for example. And since the binomial theorem is defined for all natural or non-negative integers n, I can now apply the binomial theorem here. So this is the sum from k equals 0 to infinity of, and now we've got the sum from, let's say we've got another quantity j equals 0 to k of k choose j, where k and j are both non-negative integers, but j is less than or equal to k, of x to the power of j, y to the power of k minus j. Or we could switch it around, but right now it doesn't matter. All over k factorial. What we get from this is, if we expand this, we get, this is the sum from j equals 0 to k of k factorial over, regardless of the value of j, we've always got k factorial. We can factor out k factorial. So we've got, this is the sum from k equals 0 to infinity of k factorial over k factorial, because again, this k factorial can be factored out, of the sum from j equals 0 to k of 1 x to the power of j, y to the power of k minus j over j factorial times k minus j factorial. And so we've got the sum to infinity of k equals 0, but then a subsum, if you will, j equals 0 to k of x to the power of j, y to the power of k minus j all over j factorial k minus j factorial. Now I'm going to let another quantity L equal k minus j. Okay, so now that means I've got x to the power of j over j factorial and y times, this is the sum from k equals 0 to infinity, or I plus j equals 0 to infinity, of x to the power of j over j factorial times y to the power of L over L factorial. And now again, by my binomial, and then again, since these are two megaterms in the expansion of e to the power of x and e to the power of y, and since L and j can take any value they please from 0 to infinity, By the definition of how to expand n brackets with any number of terms inside them, including infinite number of terms, this means that this is a sum to infinity. We can actually factor out my two terms. I've got a sum to infinity of j equals 0 of x to the power of j over j factorial. And then I've got another bracket with L instead of k. Because these are my megaterms and I'm reasserting my megaterms back into their original terms. Because these are clear megaterms of the expansions of e to the power of x and e to the power of y. And since there's only one unique way of me having the coefficient of x to the power of j and y to the power of L, because this is the only bracket where I can take a certain number of x's from, and each term has a different number of x's multiplied together, and the same goes for this term with a different number of y's multiplied together. So, by re-splitting my megaterms back into their original terms and factoring out those brackets, we can see that e to the power of x plus y is equal to e to the power of x times e to the power of y. And to be honest, it's probably much easier to go from this to that. And now, why is this useful? Well, say I've got my graph, y equals e to the power of x. And now I've defined it for every single possible value of x, including my infinitesimals if I really want to go that far, because x can take any value. If you use the power rule, dy by dx of x to the power of n is equal to n times x to the power of n minus 1. Correct? And now also, we've got the sum rule and the product, and not the product rule, the sum rule I'm multiplying by a constant, where you can take out the constant in differentiation. And why am I talking about differentiation here? Well, I've got a graph, and there's one final law, Maclaurin series, which is a subset from Taylor's series or Taylor's theorem, which states that, or Maclaurin series state that any function f of x that is continuous, tick, there isn't any, it's not like my old function where I had just plots and plots here. There's always a line that goes through the whole graph from all values of x, and differentiable for all values. Well, yeah, it is, but also that we can also find the nth differential of a function for all values of n. That means I can constantly differentiate a function. If that holds true, f of x is equal to f of 0 plus f, the derivative of f with respect to x of over 1 of 0 over 1 factorial plus the second derivative over 2 factorial, and then if you can find a third derivative, so the derivative of the derivative of the derivative, so say I've got f dash of x equals 2x, that means f double dash of x, or the second derivative with respect to f of x, is equal to x, or d squared y by dx squared would be not x but 2, but then d cubed y by dx cubed is equal to 0, and then every other term would just be 0 over 3 factorial plus so on and so on and so on. But it's not just times that. It's f prime of 0 over 1 factorial times x. And then here is times x squared. And here we multiply this. This is the coefficient of x cubed. And apparently if this is continuous, infinitely differentiable, Maclaurin series state that f of x is equal to the sum from k equals 0 to infinity, but or rather n equals 0 to infinity of f and f to fn of 0 over n factorial. Fn of 0 is just the nth differential. And what's brilliant about this is, well, e to the power of 0 is just equal to 1, right? So that means f of 0 equals 1. We know that that's just 1. But if f prime of x, so if the differential of a function is equal with respect to x is equal to f of x, i.e. y is equal to dy by dx, if f of x equals f prime of x, This implies that f of 0 would just equal f prime of 0, which just equal to the second derivative, which is equal to the third derivative, because, well, say I've got d by dx of f of x equals f of x. This means the second derivative with respect to x of f of x is just the first derivative with respect to f with respect to this, but that's just equal to f of x. So that means the second derivative is also equal to f of x at any point x. So that's useful. That means f of x is equal to the sum to infinity from n equals 0. Let's say f of 0 is some constant k, or just f of 0. Since f of prime of 0 is equal to f of 0, the second derivative, the third derivative, the 1500th derivative, they're all equal to f of 0, at the point f of 0, that is. That means f of x is equal to the sum to infinity of f of 0 over n factorial, times x to the power of n. And, well, here f of 0 is equal to 1. But in reality, that doesn't matter. I could just factorize out f of 0, because f of 0 is just a constant. And then we end up getting that f of x is equal to the sum from n equals 0, or even k equals 0 rather, so you can see where this is going, of x to the power of k over k factorial. Or rather, f of 0 times e to the power of x. And now, since f of 0 is just a random constant, that means the only function whose derivative can be equal to the value at that point, so i.e. the rate of change at this point, the gradient here is equal to the y value at every point of the graph. That function can only be of the form f of x equals k times e to the power of x. This implies that d by dx of e to the power of x is equal to e to the power of x, but more, and also d by dx of k e to the power of x using the multiplying by constant rule. We end up getting that this is just k times d by dx e to the power of x, and that's just the same thing. So you've got infinitely many functions that are such that if you look at the y value at any point of a graph, at some point x, and then you also look at that gradient, or the gradient of the tangent at that point of the graph, those values will always be the same. And so that can come in useful when it comes to things like modeling. This is why e to the power of x is such a useful function. And also, by using log laws, log base e of x is what is defined to be ln of x. What's so great about this is, so say I've got this y equals e to the power of x graph. How can I find out what y equals a to the power of x is for any other a, where a is not equal to e? Well, if I draw a line here at y equals a, I can then work out what the x value is. And of course, we can't exactly know what it is, but if we could dissect to infinitesimals and graph this, we would know what this graph gives us at the value a equals y value of a. By the definition of how logarithms work, this implies that e to the power of ln of x is equal to x, or e to the power of ln of a is equal to a. So in this graph, I have to this x value would have to be ln of a to give me the y value of a. If we reflect this graph in the line y equals x, we end up with the graph of y equals ln of x. And why is this useful? Well, the change of base log rule of how to get powers, which comes from this power law. Log base a of b is equal to log base a of c over log base b of c. So this implies that if I let a equal e, ln of b is equal to log base, or ln of c, the natural log of c over log base b of c. Or rather, log base b of c is equal to ln of c over ln of b. And then we can use this to find out what 2 to the power of x equals 3 is, for example. And by plugging in ln of x into x for all of these values, we can then come up with the graph y equals 2 to the power of x, or y equals 10 to the power of x. And now we can come up with our family of exponential curves, where y equals a to the power of x. And we can also work this out by finding out the derivative. Since a is equal to e to the power of ln of a, this is ln a times e to the power of ln a x. But anyway, dy by dx is equal to this times a to the power of x. And since I now know how to find ln of a graphically for all values of a, that means I can then multiply that by a to the power of x at any point x to then find out what the change at that point is and what the change at that point is, and then you can again graph it that way. E to the power of x is how we, if anything, define how all powers work. It's how I can define what 2 to the power of x equals 3 is, what the power is there. It's how I can define what 2 to the power of pi is equal to. That would just be e to the power of ln 2 times pi. And then I can plug in ln 2 times pi into x. And then since that works with the power laws and the definitions of the power laws, but also it works with e to the power of x is equal to e times e times e times dot dot times e, where we multiply x, e's together for x, all x in the natural number set, or positive integers x. Since this satisfies all of these definitions of, or requirements for the power function, this means we can actually call it e to the power of x as my power function, or rather the exponential function. And that's a proper way of defining exactly how powers work. And then from that, the natural log is the natural way of us defining how logarithms work.